So welcome everybody to today's session. We're here to talk about Marc on SimScale, and we'll be talking about how that is democratizing advanced nonlinear simulation. You may have followed that Marc on SimScale was successfully launched back in the summer, and since then there have been lots of exciting developments that we're going to update you on today. Also, if you're not familiar with Marc or SimScale, there'll also be a nice introduction to those two topics. And so to take us through that today, I'm joined here by Joanna Lee Meyer, who's a Business Development Manager for Multiphysics at Hexagon, and Richard Soka-Schuller, who's a Lead Product Manager for Structural Analysis and Physics AI here at SimScale. So welcome both Joanna and Richard. Thanks for joining us today. My name is Alex Graham. I lead product management here at SimScale, and I'm here to be your host for today's session. So please do put your questions into the chat as we go along. I should say not the chat, there's a Q&A window which you can put your questions into. I'm sure you'll have lots of interesting thoughts to share, and we'd love to get into those at the end where we'll have a dedicated live Q&A. So without further ado, I'm going to hand over to Richard, who is going to kick things off. Over to you, Richard.
Yes, hello. Hey, everyone. Thank you, Alex. Thanks for the nice introduction. And hello, Joanna. Thank you for being here again with us for a follow-up session on the Marc integration on SimScale. And in today's webinar, we're specifically focusing on the point of democratization of FEA simulation and how Marc, together with SimScale as a platform and new technologies and tools like AI, can help bring simulation to more engineers and designers. And let's quickly look at the agenda of today's webinar. We'll give you a quick introduction, set the stage, and then Joanna will introduce you to Marc, what makes it unique with respect to its nonlinear and deep physics capabilities, and why it's a very valuable new addition to the SimScale solver ecosystem. And then I'll show you around with a live demo on the SimScale platform, how we integrate Marc, what it can do on an example case. And then we're looking into what new technologies as engineering AI is unlocking in terms of bringing simulation earlier into design process, speeding up the whole design cycle. And we're wrapping up and in the end with a 10-minute Q&A session. So please post your questions whenever you have anyone. We'll try to answer all the questions at the end. Okay, so is there a new era today for accessible FEA? And I guess all of you are using today, or most of you on a regular basis, new AI-empowered tools like ChatGPT, Gemini, and others. And we could have, maybe could have made it easy to say, give the AI tool a task to present, okay, what is SimScale with Marc enabling and with AI in terms of democratization, right? And then, as you see here, Gemini spits out a nice visual comparing to the traditional way of how in the past democratization of FEA simulation was brought to the market, and on the right side, how it is now different with SimScale. I promise you this will be the last AI-generated image for today. But in essence, I think it captures well what was in the past the main paradigm, and that was the designers would be able to stay in their design tools. We would bring in some simplified simulation tools so the designers could do maybe linear, static, or frequency analysis inside the design tools. And at a certain iteration stage, it would go on to the simulation experts. They would do then the full nonlinear simulation, the detailed modeling, maybe put in some additional assumptions. And then in case they would get different results, and most likely they would get, you would start this rather slow and frictional interaction loop, right? Where the results of the detailed design doesn't show good correlation with the simplified model. Then there's design change requirements from the simulation expert to designer. The designer does the change, but then needs to wait again for the simulation expert, to have another free time to run the new updated simulation and so forth, right? So there will be meetings, there is emails back and forth, PDFs will be sent until in the end, finally, the design meets the expectations. And this is typically a rather still slow process. And in the new world, hopefully, right, all of this is much simpler. And the solution how we're proposing this is that we have an integrated platform where both the simulation expert and the designer can work. We bring high fidelity tools in this design simulation platform that are designed by the experts, right? So the workflows and the template simulations are designed by them. They have control over the simulation because it's a collaborative environment where no data has to be shared physically, so they have access on the same project. And we enrich it with AI agents that can give higher confidence to people which are no experts, maybe in nonlinear simulation, to get still meaningful, viable results out of rather complex simulations. So that is, how we see it and how it actually should already work today, and how organizations with a more modern infrastructure and software environment should already be able to make use of AI. But what we're seeing when we have surveyed mid of or end of last year 300 engineering leaders is that currently only 3% are seeing very high productivity gains through AI, right? But a lot more are seeing actually the potential for having very high productivity gains through AI. And only 7% have actually a mature AI program. When we ask, okay, what are the biggest bottlenecks for not being able to unlock the gains of productivity today, is first the siloed data infrastructure. So data cannot be accessed by AI and cannot be shared. And the legacy desktop tools are not made to work well with AI. Right, and this is actually also what we see on a daily basis with our customers or new customers that benefit a lot from having the data in the cloud, connected, available, not only to other people in their team, but also to the new AI technologies that all live in the cloud. So we have seen this on the software world already, that the productivity gains are there, and that AI has taken over the world basically in software development. Within 2 years, right, AI has come to a point where it can solve 80% of coding benchmarks. And now, iterating on software versions is super fast. In seconds, people can wipe code, even simple CAE tools. But however, on the structure or on the design phase for hardware, this impact isn't seen yet, right? So on the aerospace design, we have at least 4 weeks for simulation lead time. So the time until we have the first simulation completed and get the first insights from the initial requirements. Automotive, at least 2 weeks, and even more for electronics components design. So that's something we want to change and basically bring the hardware design iteration scale to the same level as we already see today with software. Good. For the people that haven't really heard about SimScale yet and here for the first time, we give a quick overview in a nutshell what SimScale is. A lot of data here. In essence, we have hundreds of thousands of users, millions of simulation projects completed on SimScale in the last 13 years. SimScale as a platform has always been cloud native. So from the beginning, day one, SimScale was in the cloud. So all the infrastructure is cloud native and AI ready. Collaboration is as well built in every piece of the software. It's scalable, so you can run not only small or large simulations with the same interface on through the cloud, you can also run many simulations in parallel, right? So when you want to create design of experiment studies or data for AI training, you can do it extremely fast. With broad physics, right? Structural, thermal, flow, electromagnetics. Basically, every quarter we're adding one new solver on top, so more is coming. And recently also adding physics AI, meaning instant predictions based on simulation data trained with multiple technologies, for example, graph neural networks or transformer networks, and engineering AI. Engineering AI is what we call agentic automation of workflows, and also other simpler tools like integrated chatbots in the platform. So this is what we offer with SimScale. One solver that we brought in July last year is actually Hexagon Marc, which has been extremely successful so far. And why we brought it in and why it's such a successful tool also on SimScale. That's something Joanna can hopefully tell us today and shed some light on why looking into nonlinear simulations is so important.
Thank you so much, Richard. Can you hear me now? Perfect. Why do people do nonlinear FE analysis? And as Richard mentioned before, why is there sort of such a difference when you design based on linear finite element analysis, and then when you go further down the design line, you realize that you need to completely change your design? So when we talk about a nonlinear finite element analysis, what we're really talking about is trying to capture the true behavior of the real world. Linear is a concept, a mathematical concept that was created to make things a lot more convenient. It's an approximation to make this complex the world and sort of reduce these complex problems into solvable chunks. But the real world is rarely linear, and many engineering challenges nowadays fundamentally depend on nonlinear behavior to work. And a good example is seals. Most materials, they behave differently at different temperatures. We're all familiar with this. We have materials that behave differently depending on time. So they might creep, they might soften over time, and it might also depend on loading rate. So here we can see a graph of the response of a material when you load it at different rates. When it's very fast, the blue line, it's almost linear. And when you load it at a slower rate, you can see it starts moving away from that straight line. And you can see these breakpoints here. They also move about as you get slower and slower. So capturing this is quite important. And you also get a family of materials where they can stretch significantly and not break. Some of these materials can undergo plastic yielding. And some materials I mentioned before, they'll creep and relax over long durations, and they're not the shape what you expect before. For composites, this is another good example because they might fail through different mechanisms. It might be delamination, it might be cracking, and then you have fiber pullout, and all these sometimes we'd really like to understand and incorporate and account for in our designs. When we think about material cracking, the cracks don't just initiate and then it stops there. Quite often you have a crack initiate in a material, and it's actually not a concern until it propagates to a certain size. So understanding that is also quite important for a lot of engineers when it matters. Sometimes components can undergo significant changes in shape, so they can deform a lot. The structures may buckle, and some of them might operate in a post-buckle state, or even rely on that behavior to work. So here we have an example of a buckle, and you see, the snap through function is what makes it work. Components can come into self-contact as well under large deformation, and in some assemblies, the different parts and components, they might be coming in and out of contact, and these interactions might keep changing. They might slide against each other, they might stick and then slip, or they might separate or completely lose adhesion altogether. And the friction and surface interactions, this can also evolve over time. Nonlinearity can also come about because of the loading itself. The loads may vary over time or with certain conditions. And some components might even begin their life already loaded in the loaded states, predeformed or stressed. And this can significantly affect the response under additional loading. So incorporating these nonlinear behaviors allows engineers to have a more realistic insight into the behavior of what they're trying to design, and it allows us to better optimize the designs and even sometimes innovate products that rely on exploiting that nonlinear behavior. And the other side, when we look at sort of nonlinear modeling, sometimes it's used for what-if analysis. It's crucial for safety and reliability, and it can help identify potential failure mechanisms that sometimes might be missed otherwise. And it also allows engineers to plan for failure, for it to fail in a safer mode, or for us to be able to catch it in time before it's catastrophic. So instead of relying on physical prototyping and testing, nonlinear finite element analysis allows engineers to have a more rapid and sustainable way of predicting these behavior and simulating it. So even though nonlinear analysis is incredibly powerful, it does come with a reputation. Many people think nonlinear FE, and I've heard this many, many times, is something that's difficult, it's slow, and it's sensitive to sort of the job. It's sensitive to failing. And in all honesty, there is some sort of truth to that, and I can testify to it since it's my background. The first challenge is that nonlinearities, whether they're material-related, geometric, or contact-driven, it naturally increases the complexity of the system of equations that we're trying to solve. So that is already going to take a longer time. And then with the plasticity, damage, and viscoelasticity, large deformations and buckling, and the friction contacts all added on, these introduce a lot of nonlinear and sometimes quite discontinuous responses. And that can make it difficult for the solver to converge. And that causes what people think is an instability or sensitivity. To get a solution, the solver may need lots of increments and iterations, and then that can lead to a higher computational cost. You're waiting for longer, it's taking more tokens, and etc. Computational resources as well. Sometimes we might need to refine measures, tune stabilization parameters, or tweak load steps and solver settings to get the model to converge. And quite often we have to stop the analysis and reconfigure these manually. Finding the optimum between robustness, accuracy, and computational costs, or simulation speed, depending on how you look at it, becomes a bit of a specialized skill set that people have to acquire and put the effort and time in to master. All of this results in a bottleneck. So this is why we say, while nonlinear FE is extremely powerful, it can quite often feel expensive, brittle, and very human intensive. So this is why Marc was born and has been chosen for this partnership. Marc has been around since 1971, and it was the world's first commercial nonlinear finite element analysis. And today, it has developed over the years. It offers over 30 analysis classes, whether you're diving into structural analysis on its own, thermal analysis, or a combination of both, or even including electromechanical simulations. You will find a fully coupled solution available in Marc. When it comes to nonlinear material behaviors, Marc also offers highly advanced material models that allows you to accurately simulate everything from rubber seals to space age alloys. So what makes Marc robust? And why does it have that reputation? So these are sort of the special ingredients that we have in Marc. The first one is its ability to handle contact. Marc is designed to track contact between the bodies. It automatically determines where parts are touching, how large the contact area is, the contact normals, frictional stresses, and relative sliding. All of that is automatically calculated. This is particularly important for nonlinear problems because contact is not really static at all. As the parts deform, the contact area can change. It can change quite significantly. And the contact directions can rotate, and components can come into and out of contact all the time. And Marc is built to handle exactly these evolving conditions. Marc is also designed for large deformations and large strain problems. Even when geometry changes dramatically, Marc can continuously track that contact between the bodies accurately and consistently through the simulation. Another key capability that Marc has is the automatic remeshing and rezoning. When the mesh distorts become very severe, which is very common when you have nonlinear materials, Marc can automatically adapt the mesh to maintain solution quality without any manual intervention. And when we talk about Marc taking care of things automatically, it also can take care of load stepping and increment control, which is very valuable. It will adjust the solution strategy as the physics demands it. All of this together contributes to much more robust convergence, especially for contact-dominated models that's quite often difficult to solve. So Marc has always been known to be able to solve the hardest nonlinear problems, and doing this with accuracy, robustness, and deep physics. But it's also equally important, and it's the long-term vision for us to make nonlinear simulation more accessible. Nonlinear FE has always been sort of reserved for a small group, as Richard mentioned earlier, for a small group of specialists who knows how to do it, who knows how to tune the solvers and achieve convergence. But the goal, we really want to make it available to more engineers, more teams, and to more different applications earlier in the design cycle. So that is why Marc serves as the engine under several of our tools, and now we have formed this partnership with SimScale. Later in this webinar, you'll see, and Richard has hinted at it already, you'll see what SimScale has already achieved in this space, and it is actually very impressive. They have incorporated technology to remove these barriers and reduce the setup effort to allow users to confidently explore nonlinear behavior at scale. So this is a topic that I quite like to touch on because I have spent some time looking at it. So once you have your nonlinear model working, what happens next? And I'm sure for most of you, getting that nonlinear model working and running a job is not going to be the end of your journey. For nonlinear analysis to be useful, just like linear analysis, you need to do the design space exploration. Design exploration quickly becomes much more complex than in linear analysis, and that's because there's many more parameters in play. On the material side alone, you might be dealing with plasticity laws, damage or failure, viscoelastic behavior, and each of these can introduce an additional set of variable parameters into the model. Then you have contact parameters, things like friction coefficients, which can dramatically change the system response, even with a small variation. On top of that, you then add the geometric nonlinearities, such as you might want to include imperfections, predeformed shapes, or residue stresses, as they can all influence how the structure behaves, especially when buckling and instability is involved. And of course, they're the design variables themselves, the geometry, variations, boundary conditions, load paths, and load sequences. You might want to vary those. When you put all of these together, you see the parameter space grows extremely quickly, almost exponentially. So to visualize this, I have this cube. If you have your first parameter along this x-axis here, and these are all the direct values you'd like to explore, and your second parameter along the y-axis. And then by the time you add the third dimension, the third parameter, you can see there is a lot of different permutations. And obviously for visualization here, I've represented it using a discrete representation. But when you consider this space as in reality a continuous space, the possibilities are actually infinite. So what might feel manageable in a linear context can rapidly turn into a parameter space explosion in nonlinear design exploration. Another thing that I want to mention is that in nonlinear analysis, it's fundamentally different to linear analysis because the system is path dependent. The final results doesn't just depend on the input, it depends on how you got there. The solution is influenced by things like the load history, the sequence, the order you load it, how contact evolved over time, or how plastic strain accumulates, and how the damage progressed over time through the structure. Each of those effects depend on the sequence of states that the model goes through, and not just the final load state. So if you change a parameter, even slightly, or reorder the loading cycle, you're not just shifting the results up or down, you're potentially changing the entire evolution of the system. Contact may occur earlier or later, and plasticity might localize in a different area, or damage could initiate in a completely different region to before. So for nonlinear designs, the design space could have multiple local optimas and minimas, and it could be very discontinuous, as seen on this design space here. And because of this, looking at isolated points might not be enough. You might want to look at optimizing the full behavior over time. And this state dependency multiplies the problem very quickly. Each parameter variation creates a new sequence of events and not just a new result. So we've talked about why nonlinear design exploration becomes so hard to scale. And we have a huge parameter space and path-dependent behavior running for full nonlinear simulations for every design option isn't practical. So this is where SimScale's collaboration with physics AI comes into play, and it's very powerful. The idea is to use fast physics-aware surrogate models that learn from the high-fidelity nonlinear simulations from Marc. With a few discrete data points, these surrogate models can learn and predict the outcome and generate the outcome quite quickly. So you can see here on the left, the few discrete points with physics AI mapped on top. It allows the evaluation of thousands of design variations in a fraction of time, allowing a much better coverage of the design space, and it accelerates along the design process accelerates along this discovery path to the optimized design much faster. And as we mentioned before, the nonlinear design space is highly nonlinear and discontinuous. And so with the connected solution on SimScale, users also have the option and ability to go back to Marc to validate the surrogate model prediction. So before I finish, I think I'm running out of time. I would like to thank SimScale for inviting us to join this webinar. It's been an absolute pleasure. And as Alex and Richard have mentioned, this is not my first time. And I really do enjoy joining these sessions. Thank you.
Great. Thank you, Joanna. Don't worry, we hear you again in the Q&A session at the end. But it's great to hear, all the details that in the end, in the background, come into play when we're dealing with nonlinear simulations. And it might look intimidating, but we have solutions to this, right? There is one solution that you just mentioned is the physics AI. So basically that you build surrogate models and you can actually map out the whole design space. You don't have to guess you don't have to guess where to start and where to look and where maybe not to look, where you cannot due to time constraints, right? So this allows you to be more data driven as well. And as the physics AI and the standard PDE is super integrated on SimScale, you can always at any point switch, right? Whether you want to use the full PDE solution through Marc or whether you want to have the prediction through a data-driven AI model. So with this, let's get back and maybe see some of this in action. And yeah. Okay, 1 second. I need to share my window because I want to also go back to the platform now with the demo. If you haven't seen it, what we see here is my dashboard, a folder for the webinar. There are other folders as well that I have in my dashboard. There's spaces that I share with teammates on SimScale. We see here the AI models, the physics AI models that are available to me, where I can also train new AI models, or I can also define AI agents, custom AI agents. We'll come to that later. What I want to just show you now is a rather simple, maybe not so simple, nonlinear bushing demo. So we go through the full project creation and setup process. So yeah, the start is very simple. You create a project, and as always, it starts with the CAD. We have connections to multiple design tools. For example, Onshape is directly connected, CAD native design tool, or you can import from your favorite CAD tool. What we also can do, and I've mentioned this before, we can import template simulations. So what we've talked about earlier, that there is an often in large organizations, there's the expert team and then there's the design team. And how we work a lot with customers, or how we've seen them working, is that the expert teams, they specify template simulations. So this could be now a template simulation for this bushing. For example, here, I just now import this here because it has the original part that I want. And we can remove the simulation setup again. But this would be also a normal workflow. When I would start with a template, I have a simulation setup that is already there, and I basically replace it with my current design, right? But now we don't need this because we want to start from scratch for the full setup. So we start with the bushing model, and we create a simulation. You see here we have multiple physics available, structural, flow, electromagnetics, and more to come. It's not all enabled here. But the important one today is the nonlinear mechanical powered by Marc. So we create an analysis. And you already see here, we can attach later an AI model to it, but we'll skip this for now. We set up a normal simulation from scratch. So we have, first of all, automatically generated contacts, as this is an assembly of just 2 parts. It just has 1 contact. It's a glued contact type. We can also switch to touching or whatever we want. For the glued, we can add position tolerance. For example, when we have small gaps in our model, this is essential to enable some tolerances. And then we can go and start with the material assignment. We go to the material library, just get some generic steel for now and apply it here to the hub in the middle. And for the outer part, we want to have some rubber, and we'll define it now from scratch using not a linear elastic, but a hyperelastic model. You see, we have different models available, up to complex models such as viscoplasticity that has damage, creep, plasticity, and hyperelasticity. But for now, we start with the simpler hyperelastic model with a Mooney type material. So let's just put a standard material out there, 0.6 megapascal for the first parameter, 0.15 for the second, and we add the bulk modulus of 1500 megapascal. Good. So we have our material defined. Now let's check the loading scenario. What we want to ensure here is that this bushing can, we can apply 500 Newton to it without having significant self-contact to not reduce the lifetime too much. So in this case, let's first add the fixation. We add here the boundary conditions. You see the plus. We add impose displacement on the outer surface. It's 0, you can fix it, or you can leave it free, or define a predefined value. For now, we'll leave it free, or leave it at 0. That means constrained. And here on the center, we actually want to apply a load, a 500 Newton load. For this, we use the point load. That's actually applied via a point here. We first have to generate this point. It's now default at 0, 0, but you put it back to the center of the selection. And here we go. Now for the value, we want to simply ramp the load with time. So we can really solve the nonlinear model with, in case we need multiple time steps, and it can subdivide and use an intermediate load in between to help the solver with that. And here's the load. And that's it. The only thing that we need to do, we have now the point load, but we need to connect it to the surface. That is done via a connector. We can choose between RB2, which is a rigid connector, or a deformable one, which we choose here because we don't want to add any artificial stiffness. And that's it, right? So in this case, we can go to more settings. There's the numerics. There's others. So typically you don't need to, play around with all these settings here that you don't necessarily know what exactly they mean. Our defaults are typically very reasonable and work in almost all the cases. Simulation control, right? So how long do we run until 1? 1 is representing the full load. And then here's the meshing, right? Again, also always on SimScale, we try to have very reasonable defaults, which you can change. You can go into detail. You can add here, for example, mesh refinements, other things. We see what we get with the default mesh. Okay, so now we could actually start a simulation. One thing that we now might be able to do as we're on SimScale, we can actually ask our AI agent, because you might not be sure, have we done everything correct? Is there anything we should be worried about? So we basically just ask, check the setup for issues. And this is, you can see here, we can select different models. So what we have here is the default standard engineering AI model that has a lot of knowledge about SimScale, from the documentation, from internal documents, public documents, and so forth, and therefore knows a lot. But it's also built on top of giants, right? It's built on top of Claude, so it has also, a lot of knowledge about materials, material properties, engineering in general, and this could really help us set up our simulation, right? So it says it passes all the validation checks. Which is good. That means technically we can start our simulation and should expect good results. Meanwhile, also the mesh is there. So we see automatically we generated a swept mesh with mainly hex elements that looks also good, and we're ready to go. Now actually I see that it has a material unit issue. So I seem to have used Pascal and not changed it to megapascal in the C01. So let's go back, see the rubber, and indeed I use 0.15 Pascal. So it recognized that this is probably not what I have intended. Good that we captured it, and we're good to go. One thing I wanted to maybe also do is capture the results at this remote point where I applied a load, right? So for example, I could get the reaction forces, the displacements, and so forth. In this case, I just get all and start the simulation. Now, as we're cloud native, this runs on the cloud, not on my computer. I could run now 10 other simulations with different load values or different constraints. In the simulation control, we can choose actually how large the instance should be. I think typically we use 16 cores for the typical mesh sizes we get, but you can use up to 192 cores, all with the same license on SimScale, right? Between 1 and 192. Okay, we don't have to wait here. I have another setup that is completed, right? It uses also the 500 Newton force value. And if you check the solution fields, it took 4 minutes. That's what we get here in the setup. Maybe we reload it. We have an integrated pulse processor in SimScale, so we can assess, the stresses, strains, results. You can here maybe look at the von Mises stress if that's within reasonable ranges. And what we can see here, there's some self-contact, right? So what we could do now is maybe redesign a bit. So we go back to our simulation that is still in progress. And actually now do one thing, and that is we duplicate the simulation. So we leave the original one untouched, and then we edit our CAD model. And what we want to do is basically just thicken the internal part here. So we pick one face, and then we have some tools, for example, to expand tangent faces. So we have the whole pocket here, and we again expand now for same area. So we should get all the pockets. Okay, now we just thicken it with the move by maybe 0.5 millimeter. And see, yep. Okay, so that should be it already. And I save my new design and simply go into the second simulation, and maybe I rename it. And just replace the CAD. So now all the boundary conditions is reassigned from the old to the new model. It's associative, nothing needs to be changed. And I can simply run the new analysis and go. Right, we also see now that the meshes need to rerun on the new geometry because it changed. And also now we have the old and the new simulation running in parallel without any load on my computer. If you go into people that have been using this already and are more interested in new features, what we can now do actually is, let's assume we have now applied the force load. We will also want to do a rotation, right, around the center hub here after the load is applied. So we apply first 500 Newton and then apply 45-degree rotation. How can we do that? So simple as that, we just apply a point displacement, for example, here, and apply it on the same point in the center and give it a time-dependent rotation. But now we just don't want to start at 0, but we start at 1 and let it run until 2. And the rotation should be around the y-axis and go to 45 degrees. You can check if that's set up correctly in the graph. Yes. Okay. What we also want to do is we don't want to define this restriction here throughout the full analysis, right? Because otherwise we couldn't apply the force. We want to first let it free, apply the force, then fix it in space and rotate it. So what we need to do is we need to activate load stepping. So we create a first load step, which we call force. The force load step will go until 1 second. And then we have a second load step, which is called, let's say, rotation, where we will apply from 1 to 2 seconds the rotation. So we here go there and assign the rotation only for this point displacement. And then we go back to our point load, our force, activate load steps, and tell it to only apply the force here in the force load step, right? So what we have done now is the first load step, we move it in place with 500 Newton, then we lock it and rotate it by 45 degrees. The only thing that we need to adjust is let it run actually until 2 seconds, where the full simulation is done, and maybe make it a bit faster by computing less increments. And we also start the simulation now. Okay, so that's basically it. So far, what we've done is we run the first design with 500 Newton, the second design with 500 Newton, and also applied a new load step. and it's all running in the same time, not on my computer. That's the most important thing. If you now want to check the results, we go back into the completed project, so we don't have to wait. Look actually at the data to see, for example, the rotation, if it's properly applied. So we see the initial force until 1 second had already resulted in some rotation, right? So 2.6 degree, and then on top we added another 45 degrees, right? So we see that also we have here a reaction moment that was applied, that came into life after we have fixed the part and applied a predefined rotation. Let's see how this actually looks when we look at it in the 3D viewer, in the post processor. So that's it. Maybe we can let it run in the animation and see if it actually works as expected. In the meantime, while we see this load, don't forget to post questions into the questions functionality. We'll answer them later. So we activate the mesh to just see a bit better the rotation, and we can actually see first the movement due to the force, then the rotation is applied. Okay, so this went maybe a bit longer than I hoped, but I hope this gave you a good overview on how simple it is to work with SimScale with Marc. What we have seen actually is a very complex analysis from a physics point of view. It had nonlinear materials and it had self-contact with friction, not the easiest to solve with standard tool. Here it just went without any issues. And the good thing, we used the engineering AI agent to help us to find a mistake, actually. Right, so we messed up, or I messed up the unit, and it got it right. So yeah, I've showed mainly everything already, just maybe the highlights from the last half year, what we enabled for Marc on SimScale. First, the automatic contact detection now is enabled for large assemblies as well, right? If you have hundreds of parts, you don't want to define these contacts manually. We have automatic contact detection now that runs on cases with thousands of bodies. We have new hyperelastic material models. For example, the Marlow material model is very easy to use when you have test data. You don't need to fit, do any parameter fitting. You can use more or less directly the data that comes from the testing. And we have more advanced models, right? So here the viscoplastic model, it can have damage, creep, and other phenomena modeled in it, and specifically interesting for modeling plastics, for thermoplastics and elastomer materials. Yeah, and the connector points we have seen very useful to guide loads or displacements or rotations in complex manners. Okay, so now the last step, we have only a few minutes left, and I try to make it short, but it's important. The first step that we did now, we have now complex simulation in the cloud. It's easy to access. We can run, complex models. But the next stage is actually to package this in a way where we can effectively work with it when we need it and we need to save time. And for this, what we've built is agentic AI included in the SimScale. We have already seen some of this with the chatbot, but the chatbot is basically just on the surface the technology. It's much deeper than that and unlocks much more use cases than just a simple chatbot. So what the engineering AI does is it shortens the time until you have your first simulation. Right, that might be in the end just a single click. Once you have the new CAD, you say evaluate, and it does all the setup according to what you defined it should do, and it can adjust to changes in the CAD. Right, it's not as rigid as a fixed script in a traditional sense. And the second part is the cycle time that is sped up with physics AI, right? So you can actually explore the full design space. So what we can do when we take basically the agent and customize it for a specific use case, right? And not ask in a chat manner, but actually predefine what it should do. based on internal documents, based on RFQ documents, load case specification, and so on. We can just update a new CAD and say, okay, what is the peak stress here, right? Or what are the eigenfrequencies of the inverter according, to our internal specifications regarding materials, regarding constraints, regarding everything that is specific to your use case. Or what is the CV value of the valve, right? And let's see if you have time to also see this in action here on a different example. So here I have a gearbox, and you can see it's rather complex because it has multiple bolts. Even if you have a bolt preload, it takes quite some time to manually define it. So we go back to the AI agent, and this time we don't use the standard agent, the generic one, the engineering AI agent, but we use a specific one for our fictitious company that builds gearboxes and does just the gearbox analysis, static analysis, right? So this is the gearbox assessment agent. We can define it actually in the dashboard. I don't show it now. So basically there you can define exactly what it should do. In this case, we just say it should set up static gearbox. Okay. And that's it. So it already knows what to do. We could also just say go, because internally the agent is defined to assess now the geometry, check the bolts, check the different parts, assess what they are, and then define the different materials, apply to it, define bolt preloads, define fixtures, also define the gear loads, and then run the study, right? So we see now this is live, right? So I can still interact with it, but it actually now sets up autonomously the simulation, right? So it has now defined the static analysis. It has already added the contacts. Now it's assessed that it has 78 components and so forth. So this will go on for some time. If it's in the UI, it's actually not the fastest. We have here in the video, maybe we can speed it up a bit to show the process, what it actually does, right? So here we asked also to show the bolts, right? It showed the bolts, it could assess them. It has internal documentation how to define the bolt preloads according to which specification it should define them. And in the end, right, we don't have to interact at all with the model. We just write what we want it to do. And then it will, in the end, set up the simulation and we have a result, right? So this is the next level of automation. And we could even go one step further, right? With instead of typing the stages always in, we go the next stage and say we have a custom interface, right? Something that you could build, for example, with vibe coding, a completely abstracted interface where through the API, an agent or our AI agent is actually running the whole study. The only thing it needs a PDF or some input to define what it should do, what are the specific requirements for this model. So now this one is one that designs bike frames, right? So it starts with an RFQ document with some new bike design it should produce, which load cases to run, and what are the limits for the stresses and displacements that are acceptable. And then a CAD file, right? So a starting CAD design, the initial design. So these two are the inputs. And then you basically just let it run, right? So it can just say review the details, or you launch the full simulation report already, right? If everything looks fine on the input, you are good to go. You launch the simulation. And it will actually set up the simulation. We can see this now here to start. It launches the simulation, finalizes it, and then checks it against the references that come from the RFQ document. Right. So we see here the stress is 65 megapascal, whereas it should be a maximum, or the other way around. It's more than 90. It should only be 65. So the agent puts out some recommendations: addition of a bracing tube, increase the cross section, and then you can, either say, okay, whatever, it's okay for now, we use the existing results, or we say, okay, do the changes as proposed, generate a new design. If the design is, for example, connected to Onshape, right, where Onshape has a parametric design, that's super easy to do. And then we have the new adjusted design that has the additional bracing, and we run another iteration, and hopefully that one is then in line with the requirements, and we generate the final report. So I think this is the final stage where we can go already now to really have a complete product for a specific use case. But right, that's not always the best use case. Sometimes people want more flexibility. It doesn't, it's not necessary to customize that specifically. So therefore, we have all the other abstraction layers that we've just shown before. So now, last minute, quick overview. I can take a screenshot as we're going through this too fast. This is currently how our roadmap for Marc on SimScale looks like. What we're highly, with highest prior currently working on is the thermomechanical analysis, the coupled thermomechanical, right? So coupling, not only chaining the thermal and mechanical effects. This will be released in its first version by the end of this quarter. And then we are adding, many features every quarter. Here's the most important ones. For example, dynamics analysis in Q3, temperature-dependent materials Q2, and so forth. So lots of new good things coming. At some point, hopefully, towards the end of the year, also adaptive mesh refinement, so you can really unlock the extremely nonlinear large deformation cases that Joanna mentioned earlier. Okay, so maybe, summary, I think that's okay. We can quickly try to answer some questions at least. Sorry, I went really overboard.
That's okay. Thanks very much. I mean, I think it's lots of very interesting material to go through there. So I think it's good to take the time, and I think the audience is also interested in it as well. One thing to mention is, of course, that we will be able to provide a copy of the slide deck afterwards, so you'll be able to have a little bit more time to review some of those slides, particularly about the recently released functionality. Of course, we are basically out of time, but I mean, we have had some questions in. It'd be great if we could just address some of maybe the most kind of urgent ones. So a couple just about accessibility. So like, who actually has access to Marc in terms of SimScale users and Marc users? So maybe that's one for Richard quickly. Oh, you're muted.
Yeah, so you can trial Marc for free. So if you have a community account, it's enabled for test simulations. You can run 10 simulations with Marc to see if it's fitting your needs or not. If you're a customer, you can also ask us, and we can set up a trial for you. Yeah.
Okay. Thanks. Yes. What else we had here? The CAD, there was one about CAD import. So which, in particular about CATIA, there was a question about, can I import CATIA CAD models into SimScale?
Yes, CATIA, all the major CAD formats, CATIA, SolidWorks, Autodesk Inventor, Creo, all are available. Also neutral formats, IGES, STEP are there. Great. I see one more question regarding the surrogate modeling. Also quickly, because we couldn't really get to this today. For the surrogate modeling, we do it very similar to with the solvers on SimScale. We have multiple solvers, FEA solvers, even we have multiple, CFD as well, and we have multiple surrogate modeling tools available. One is Navasto, one is NVIDIA Physics Nemo, and there is one new coming soon. We'll talk about that soon, hopefully also publicly. And then we'll have at least 3 different technologies that we can use for surrogate modeling. Most of them are purely data driven. So you're running a lot of, you set up the simulations on SimScale. You can run batch simulations either in the UI or with the API. And we have an interface how you can actually train the models on SimScale and use the surrogate model. Maybe I can answer via email. We have also webinars specifically on the surrogate modeling.
Thanks, great. Yeah, maybe one final question for Joanna. So somebody was asking about like how to know whether a particular problem is suitable for running on SimScale versus running on kind of the full Marc product. So how would you advise people in that situation?
Yeah, so I think at the moment there's certain functionalities that's still only available in Marc, but Richard did show the roadmap. So I think depending on when you need a certain functionality, I guess you have your two choices to choose from.
And I guess maybe also who the user would be, or whether it's a team of users or a more of like a specialist kind of role. Would that be relevant?
Yeah, so I'd say if you're a sort of seasoned FE user and you don't want a cloud-based application, then getting an on-premise Marc might benefit you. But yeah, if you want sort of to benefit from what SimScale has done, to have that easy setup of the models, to have that consistency and templated sort of ability, then yeah, SimScale is definitely there for you to explore. Now to encourage it.
Awesome, thanks. Great, yeah. So I'm afraid we've gone over. Apologies for that, everybody. But thank you for bearing with us. Of course, if you have questions, you can reach out to either Richard or Joanna or myself. You can find all of us on LinkedIn very easily. And yeah, we'll be following up with a recording and a slide deck afterwards. So yeah, thank you very much for your attention and all of your questions. We'll follow up with any questions that we didn't get a chance to cover as well directly. Yeah, and with that, thank you very much for joining, and we look forward to seeing you next time.
Yeah, thank you, Joanna, and also thank you, Alex, for hosting. It was a pleasure again, and thanks for everyone watching today. Let us know if you have further questions. We're happy to answer also more detailed ones.
Awesome.
Thank you, everybody.
Goodbye.